Hello and welcome. So on this video, I'd like to explore the electromagnetic spectrum from the lowest wavelength to the highest, which is essentially a tour of the frequencies of light. As a quick refresher, light is a synchronized oscillation of an electric and magnetic field emitted from charged particle accelerating, or photon, as seen by quantum physics, carrying no mass and no charge, traveling at the speed of light. They do interact with matter in different ways, largely depending on their energy or frequency, as we will see. So to begin this wavelength tour, let's take a look at a photon in the ELF and VLF region of the spectrum. These guys are oscillating from below 1 to 100 kilometers, which puts its frequency in the audible spectrum. So with a long antenna directly plugged in into your sound card, and with some amplification with a software like Spectrum Lab, and many other sound spectrum analyzer available online, you could totally pick it up. They require very large antenna, and some have taken advantage of long metal fans to transmit and receive on these wavelengths. Because they have the advantage to penetrate seawater, they have been used to communicate with submarine. But because of the extremely low rate of data exchange and very large antenna requirement, their usage is very limited. Next is the somewhat more familiar HF, VHF, and UHF. You already know about VHF every time you tune to your local radio station. Radio amateur also communicate in this wavelength, as well as two-way radio, pilots, weather satellite. Your GPS receiver is tuned to receive from this area of the spectrum, the space station, and even some space probe. I have been messing with various receivers and antenna for a few years now, trying to pick up some of these signals, and this may be the subject for a future video. Maybe. So far, all these frequencies are long enough to get around obstacle, which is what we want for long distance communication. But even the strongest emitter cannot produce RF to interact with anything outside of an antenna. But that will change with the next higher frequency. I am sure everyone watching this video is familiar with a microwave oven. This is a small yet powerful radio transmitter, broadcasting wavelength small enough to interact with small molecules like water. Here you can see how much power is detectable from a small crack in my home microwave oven. Also, most cell phone, Wi-Fi, and Bluetooth broadcast in this region as well. Moving up a notch, the infrared allows us to see where heat is being produced. This is my house, invisible at night, and here in infrared. Here's my cat, invisible and infrared. And now we can see how glass is stopping most infrared from detection. Now, unless you are blind from birth and just listening to these videos audio, you already know about the visible spectrum. But our eyes are deceiving us and only showing us a blended view of all the frequencies from about 380 to 740 nanometers, or about 430 to 770 terahertz, which is about 1 trillion hertz, or 10 to the power of 12. As a side note, the colors we see a combination of absorption and emission from the atoms that makes up the world around us. Only the outermost shell of these atoms are usually involved in those exchanges, and these can be seen in the emission spectrum of various gases in the right condition, like in the fluorescent light bulb. Analytical technique like atomic absorption, ICP-OES, and other lab equipment take advantage of these properties for common lab analysis. I've covered this in a previous video, link in the description. UV light carries even more energy, and because of its wavelength, about the size of an atom, it can trigger chemical reaction that would otherwise not normally happen, like the famous hydrogen and chlorine reaction.
Ultraviolet. Boom.
There is no way to distinguish between hard UV and soft X-rays, other than the mean of production. But beyond ultraviolet, light carries enough energy to ionize atoms and molecules. These ionizing radiation have enough energy to penetrate deep into various material and are used notoriously as such. They also have sufficient energy with their short wavelength to reach deep into the electron shell and knock off electron from the K, L, and M shell, which is an advantage for XRF in analytical chemistry. Just like with ultraviolet, the difference between X-rays and gamma rays is solely determined by the mean of production. Radioactive substances produce radiation with very short wavelength, called gamma rays. These photons have very specific wavelength that permits the identification of said radioisotope. Here, cesium-137 with its lonely peak. At this point, wavelength and frequencies are meaningless, and we talk in terms of energy, specifically electrovolt, or thousands or millions of electrovolts, keV and MeV. Above 10 to 15 MeV, light has enough energy to penetrate within the nucleus of an atom and exciting it enough, thereby rendering it radioactive. So I hope you enjoyed this quick tour of the electromagnetic spectrum. Thumbs up if you did. Let me know what you think in the comment. Constructive criticism is always welcome. Rate and subscribe if you feel like it. Check out my Patreon, and I will see you on the next one. Thanks for watching.